right, gang. How's the homework? All right. Yeah. Cool. If you're having fun, that's a good thing. So if you think about it, probably if you looked at perms, you're using perms, right? The function perms. All right. So the function perms, of course, if you think about it, is not efficient, right? In what sense? Can anybody say in what sense is it not efficient to use perms?
Repeat.
Yeah.
And you run through different loops at the same time. Like
Exactly. Right? Because if you shift the starting point, you can have the same loop, right? Like 1, 2, 3, 4 is the same as 4, 3, 2, 1, let's say, for example. All right? So, but that's not the point of this. Efficiency is not if you're having fun with it and you're finding ways of trying to speed it up, then that's great, right? But that's not the main point of this. The main point of this is, again, to get the rust off and to, anyway, even if you were able to speed it up, once n gets too large, even the time that you speed it up would still take too long. Okay, so we need other tools. All right, so let's see. So there's no questions on the homework or anything? Okay, so let's continue with least squares and looking at it from a different perspective than you've seen it before. Okay, so we're back to this. We started off with this problem. You have data points, and we're trying to fit y equals mxi plus b, and we're trying to get as close, right? So here's a point, and this is the residual ri, which is equal to mxi plus b minus yi. Okay, so that point is xi comma yi. So the residual is the error, right? And what we're trying to do is we're trying to find a solution that minimizes the sum of the residual squared. Are we on the same page there? Okay. So really, this is what we call an unconstrained optimization problem, because we're really minimizing. We want to find a solution. And when I say find a solution, what am I looking for? What is the thing I'm trying to solve for?
B.
M and B, right? Okay. So minimize over M and B, okay, the sum of the residual squared, sum I equals 1 to n of the residual squared, which is also equal to the sum of this mxi plus b minus yi quantity squared. Okay, and we're actually, just for mathematical cleanliness, I'm going to throw a 1/2 on there. Okay, only because when I take the derivative of a squared, I get a 2 times, right? So this just cleans it up. It gets rid of the 2. You buying that? So it's very common. Would everybody agree that my optimal solution, the value is going to be this value, this cost. I'm going to call this j, the cost function. Okay, so this is unconstrained. We're just minimizing a function that's unconstrained. Okay, would you agree that the cost will be obviously half of the cost without the 1/2? But would everybody agree that the place, if you think of a bowl or even a parabola, would you agree that if I multiply by 1/2, it doesn't change the point at where the minimum is? You buy that? I mean, I can prove it to you, and we'll do it at another later date. But as long as you intuitively can buy that, then throwing a 1/2 doesn't do anything to the optimal solution. It just changes the cost function, the value. Okay? So, now again, what was the intuition with trying to find M and B so that it minimizes the residual squares rather than just the residuals? What was the intuition behind that? I mean, why am I not just summing the residuals and minimizing that? Yeah?
It has a closed form solution.
Okay, one thing is it does have a closed form solution. What else? Yeah?
Because positive and negatives could offset each other, give you a false zero error.
Well, exactly. We don't want any negative. We want we want a 0 as our minimum. All right, that's the best, where all the solutions. So we square it, or we take the absolute value. Those are the two choices. But absolute value doesn't have a closed form. We'll come back to that. Okay. So at this point, we're taking some of the squares, and we're going to minimize that. All right. So think of this. Really, this is a bowl because it's a quadratic, and it's got two axes. It's got an m-axis and a b-axis. And if you think about it, if you find the minimum, so it's a bowl, right? You slice it, there's m and b. If you can find a b that minimizes and then an m that minimizes, that point is going to be the bottom of my well. Are you buying that? Okay. So that's where those equations came from. You take the derivative, del j, del b, and del j, del m, and you solve those to get, so if I do del j, del m equals 0, and del j, del b equals 0. If I solve these two, I can get that funky m and b equation that I showed you at the end of the last lecture. We on the same page? Cool? Stop me. Okay. All right, so that's one way to look at it. But I want to look at it from a linear algebra perspective, okay, not an element-by-element perspective. All right, so let's put this into linear algebra form. Okay, so let's talk about the residuals. So the residuals, if I put it into a matrix, so let's say linear, I'm going to say linear algebra form. Okay, now the residuals are, and I'm just going to list them. All my residuals are mx1 plus b minus y1, mx2 plus b minus y2, dot, 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 mxn, hold on a second, let's see. Yeah, mxn plus, because we're assuming there are n data points, let's say, okay? mxn or xm, it doesn't really matter, plus b minus yn. We okay with that? I'm just listing them, okay? Now I'm going to try to pull out my variables so they sort of look like ax equals b, okay? So, or ax. So the residual, would everybody agree that if I pull out my variables, m and b, what's my first row going to be? And let's do minus anything. So anything that's not multiplied by a variable or a linear function of the variables, I'm going to leave over here. So I'm going to put y1, y2, dot, 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 all the way to yn. Okay? And I'm going to call this, I hate to use, just for simplicity, because I like using ax equals b. So is everybody okay if I change b to the y-intercept b to be different than this b, right? So I'm not confusing you guys. So I'm going to do d. Is everybody okay with that? If I change b to d in the y-intercept? Sure, I don't want to confuse anybody here. Okay, I'm just going to change, so it's mx, so d is now my y-intercept. If I do something like this and you're confused, stop me. All right. So mx plus d is my line. So now, what do I put in my first row?
X1 plus 1.
X1, good. And then,
That's 1.
so x2, 1, dot, 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 xn, 1. This is my A matrix. This is my x. So now what I want to do is, would everybody agree that what I'd love is that ax minus b equals 0? You agree with that? I mean, that's what I want. Of course, I can't have that, but that's what I want. Okay? And of course, if I move b to the other side, I get ax equals b. Okay? All right. Since I can't do that, then what I'm going to do is I'm going to minimize the sum of the residuals. Okay? Sum of the residuals squared. Well, guess what? That's something we know in linear algebra terms. How could I write that? Sum of ri squared, we already saw it in last lecture when we talked about linear algebra, what's the sum of ri squared in vector form? So if I want to put it, if I wanted to use r, how would I rewrite this? What's that?
R times R transpose.
Or r transpose r. Because again, r is assumed to be a column, so, okay? R transpose r. Are we okay with that? The sum of, right? That's going to be the element squared. Or I can rewrite it as the 2 norm of r. That's also squared. Okay? But I'd like to focus on this. All right. So here's what we're going to do. We're going to plug in ax minus b for the residual into the r transpose r. But before we go on, are we okay that the sum of ri squared is the inner product, or the inner product of r with r? It's a vector. Okay. R transpose r. So what we really want to do is minimize ax minus b transpose ax minus b. Okay? Yeah? All right. Clean it up. Get it down. I want you to simplify it. Okay? Multiply them together, takes the transpose, multiply them out, and then get them all into individual terms. Okay? Do the algebra. Just write it out. Not factored. But what's the opposite of factoring? Expand. Thank you. I'm like, defactor? Expand that. Thank you. Okay. Well, how many people got that? Okay. If you just do the FOIL after you transpose the first one, then you get that. Okay? I'll give you a chance to look at it, or you can re-look at it later. Okay. So, now, here's a question. Is this a matrix, a vector, or a scalar?
Scalar.
It's a scalar, right? You know that just from the beginning. Without even looking at that, you know it's the sum of the residuals, and those are sum of numbers squared, and it's a scalar, right? But we can double check it, right? We can check each component. Well, this is an inner product, so we know an inner product is a scalar. This, well, you can also look at it. Would you agree that A times X is another vector? So B transpose times another vector is another inner product. So that's a scalar, and etc., right? And then same thing over here. Would everybody agree AX is a vector, and this is AX transpose, so it's vector transpose, so you get a scalar again. Okay? Okay. So now, what's our goal? Well, again, we're trying to find what? What are we trying to find? We're trying to minimize over what?
M and B.
Well, in this case, M and B are gone. Where are they?
X.
They're in X. So now we've forgotten about M. Forget about M and B. Yes, M and B are inside of X, but at this point, we're now just worried about X. We're trying to find X such that what? Such that this cost function is minimized. Again, we're doing the same thing, all right? But now, what this allows us to go bigger space than 2, right? We were worried about, when we did least squares, we're doing 2-dimension M and B. But now, we're going to move on past 2, and we're going to move to whatever, n-dimensional variables, okay? So that's why getting it in X could be 2 long, which is M and B, or it could be 50 long. You agree? Now we've got it. That's why this nice linear algebra notation allows for much bigger problems. With me? Okay. So now what do we want to do? Well, again, this is J. This is the cost function. All right. What we want to do is we want to take the derivative with respect to X. Okay. Well, it turns out, of course, this is linear algebra, so we're going to take the gradient. Is the same thing. So the gradient with respect to X of J, okay, is really just equal to del J del X1, del J del X2, dot, 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 and set this equal to 0. Okay? what is x1 and x2 and x3 and x4? What is that in this problem? Yeah, x1 is m, x2 is b. In this case, there's no x3, no x4. We just have x1 and x2. Okay, so we're doing exactly the same thing, all right? But this time, we can use linear algebra calculus to quickly take the derivative of this, okay? So I'll just point you to the back of Professor Vandenberg's and Boyd's book, Convex Optimization. There's a whole appendix on taking derivatives of cost functions that are in linear algebra 4, okay? But I'll just do it real quick. And this is, turns out, oh, don't forget the 1/2. The 1/2 will help clean up. That's just that multiple. So even in matrix form, you get a 2 because of this guy. This times this is actually the 2 norm squared. Okay? So it turns out, if I take the derivative, it actually becomes, oh, you know what I'm going to do? Sorry. Before I step into that, there's one thing I wanted to do. I wanted to collect these two terms. So would you agree that these two terms are the same? This term and this term look different, right? But they're not. How do you know that? So actually, they both become minus B transpose AX. Okay? How do we know that? Was that? No, it doesn't equal B. Nope. We want it to be equal B, but it's not. Right? This is least squares. The equations don't, AX does not equal B. But we're trying to get it as close to B as we can. Right? That's the whole point. How do I know those two are, the combination of them becomes minus 2 B transpose AX? Yeah? Well, if you take the transpose of one of those two, it becomes the other, right? But why can't I take the transpose and not change it? Yeah. Because it's a scalar. It's dimension 1. So I can take the transpose and it does, so I can take the transpose of any of those and it doesn't change it. Does that make sense? All right. So that combines, so what we get is finally, so I'm just going to combine those as minus 2 B transpose A. Okay. So now I'm going to set it equal to 0, and let me go to the next page, and I'll write down what the calculus comes out to be. So, or I'll just write it right here, actually. So the derivative becomes A transpose A X minus A transpose B equals 0. Okay? Now, notice there's no B transpose B. Why did that disappear? So all that was left was A transpose A right here and an A transpose B. Where is the B transpose B? Where did that disappear to? Yeah. What was that? It has no x in it, right? So the derivative with respect to x, it's a constant, so gone. Okay? So now we get down to A transpose A, x is equal to A transpose B, okay? And this has a name to it. It's called the normal equation. And I'll explain to you why it's called the normal equation. But let's just... Yes?
Where did the 2 go?
From the 1/2.
Oh, okay.
So the 1/2, so I get, this is actually a squared. So when you take the derivative, the 2 cancels, and then the 1/2 comes and cancels that too.
Okay.
That's why, again, the 1/2 is a nice for just cleaning up the 2's. Okay? I could have left it and then divided by 2 to get, it would disappear. Okay? Questions? Okay. Now, let's solve for x. So, we're back to A transpose A, x equals A transpose B. So, that gives us x star equals A transpose A inverse A transpose B, which is also written as A dagger, which is B, where this is known as the pseudo inverse. Okay, so remember, would you agree that I want this? This is what I want. Okay? I want AX to be equal to B, so if I can solve, to find X, I would take A inverse times B, right? This is what I want. I want X equals to A inverse B. But can I take the inverse? No, I can't take the inverse, because why? It's not square. It's tall. Right? It's got a column of x's, it's got a column of 1's. So I can't take the inverse. But if I take, and this is why they call this the pseudo-inverse, because this piece right here, that's the pseudo-inverse. Okay? Because it's sort of doing, it's doing it as close as possible to A inverse, in the least square sense. Does that make sense? Okay? Questions? So that's it. That is the least squares solution, closed form. If I can put my A, if I can build my A, and in my case, in the regular data fitting a line through data, my first row of A is all my X data that I'm given. My second row is just 1's. My B is all my Y data. Now I can just do this. And I get, and what's my solution X star going to give me? Well, let me ask you a question. How many elements are there in X? 2. And the first element is, and the second element is B. That's it. All right? So the cool thing is again, this moves beyond, this works for 2 dimensions, but we can move on past 2. Okay? So, let's play with Matlab. Questions more questions? Did that make sense? The hard part is getting it into this AX, getting the residual into AX minus B. Okay? Once you get it in there, then you're done. Okay? Let's look at this. Let's play with Matlab for a second. Uh-oh. Why is it? I don't know. Is it not? Oh, seriously? It's like every time I connect this. This is not good. I need to use Matlab a lot here. Okay, let's take a second. Oh, come on. This is annoying. Okay. So, give me an example of where you would, give me an example of least squares or fitting data, but you've moved past M and B. You've moved past, or I should say not M and B, but 2 dimensions. Okay? Give me an example of data fitting that you've moved past 2 dimensions. Yeah.
The example you gave us in the first day where we had 3 different products we're trying to make at different prices. Be 3-dimensional, right?
Well, that wasn't a least squares problem because you weren't minimizing. So this is a different problem. Least squares, let's put it this way. How do we say this? Different problem. Could I set that up as a square? There's no need to put it into squares, but I guess we'll come back to that. But in terms of just points, just literally a scatter of data. Okay, where do we get bigger than second or size 2x? Yeah.
Talking about something that's like maybe you have XYZ data and you're trying to fit it like a surface to it, or is that?
So that's possible. You could even do it in 2D. I'd have to think about it in 3D. That's possible. Even in 2D. Yeah.
If it's a higher order polynomial?
So higher order polynomial. So meaning I've got more than m and b. Now let's get rid of m and b. Let's just give coefficients in front of constants, right? So my function is no longer like a1x plus a2, which is a linear function. My function that I'm trying to fit is now a1x squared or a1x cubed plus a2x squared plus a3x plus a4. So what order is that now? 4, right? Because I got 4 variables that I'm looking for. Now remember, x is not my the xi's are not my variables because those are the data I'm given. It's the coefficients are actually my new x vector. Okay? Let's see if we can. Okay. So let's see. Let's run. Oh, what happened? Died on me. All right, that's fine. Okay. So all I'm going to do is I'm just making noisy data. All right. I'm fitting. So this is. Let's just go back to M and B, fitting the line through data, and then we'll go higher. Okay. So my M is 4, my B is minus 10, and then I just add noisy data. Okay. I just added. You can see down here. My Y is now noisy. Okay. Make sense? And then I plot them, and then I can do outliers, and I'll just comment those out so that they're no longer, there's no outliers at this point. They're just noisy data. So let me run. Okay, so here's our noisy data, right? Does everybody see it's sort of, again, maybe I put too much noise. I could reduce the noise, all right, but let's just leave it, okay? So it's sort of, you could see that it's sort of the original line fits through there. So the goal is we're trying to get back to the original line, right? Or the original M and B by this data. So one thing I could do is I could just use Matlab's internal function, all right? So if I go help polyfit, I think it's polyfit. And I've got my X and my Y too. Those are my data. Oh. Okay. So here's my polyfit. So I'm going to give them, so it's going to give me my polynomials, and I'm going to give it the X data, the Y data, and then the order, right? So in my case, I want order 2. Order 1. I want order 1. I want a first order polynomial. So here's what we're going to do. P equals polyfit. And I'm going to give it my X data, my Y data, and then 1. Okay, so not very good. Let's see if we could, sorry. Let me reduce the noise maybe. Let's see. Where's my noise? Like 1. I'll reduce it by a lot just to see that it works. Okay, so that's quite a bit less noise, right? And I'm going to do polyfit again, and we're much closer, right? We're much closer to 4 and minus 10. Agreed? So it's working. The more noise, of course, the harder it is to get back. Let's do a little bit more noise. Let's see. Okay. So the internal function, now of course, the internal function is using least squares. All right, so let's just compare our least squares. So if I do that. All right, so here's the solution polyfit gives us. Now let's try to use the new technique we learned, right? So I got to make my A matrix, right? A is equal to, and my X, I think my X is in a row vector, so I got to make sure, I got to transpose it. Okay, so it's column. And then I'm going to do ones of rows length of X, comma, 1 column. Cool? With me on that? Oh, what happened? Let's see. So maybe it was in a, okay, there it was. It was actually a column. How are we doing? We cool on that? Okay, so now, what's my b? It's just equal to my y, right? And now what I'm going to do is, well, I'm going to do a couple of things. So first thing I'm going to do is I'm going to go A inverse of A transpose times A transpose times B. Okay, so now, let's double check that. Okay. Believe me now? Okay. Now, of course, Matlab has its own pseudo-inverse also, so I could go P-inv of A times B. Give you the same thing. Okay? And the other way to do it is the slash. We'll also give it to you. All right. Now, you got to be careful with the slash. It turns out, here's what the slash does. The slash will figure out the best, whatever it thinks is the best choice to invert the matrix. Now, if it's square, A slash B is going to do inverse. Although the beauty is it's going to use fancy factorization that is the most efficient. Okay, like QR, LU, whatever. It's going to figure out the best way to do it. Okay. So, in fact, when you do A slash B, you're saying to Matlab, don't worry about actually calculating the inverse. I don't care about the inverse. I just care about the solution. Does that make sense? So that's where factorization comes in. If you go inv A times B, then you're actually saying calculate the inverse, which is much more costly than LU factorization. Does that coming back a little bit? Okay. It's beyond what we want to talk about, just a little tidbits. Okay. Nuggets of information. Don't look excited. Okay. So, I'm doing my best here. So, okay. So the A slash B, you can use it for inverse, you can use it for, and it'll just do it for you, but you have to know what you're doing. For example, it happens to be that A slash B and P inverse times A, or P inverse times B, gives you the same solution only for least squares. I'm going to teach you least norm here in a little bit. Next lecture probably will start with least norm. Those aren't the same. P inv A times B will not give you the same solution as A slash B when we're doing least norm. Okay? So best to use what you know and understand it rather than just throw out A slash B. Okay? Although A slash B is very, very good. Okay. Okay. Let's look at higher order. So let's go back to Inkbook. Any questions? No? Okay. All right. So as I was saying, now that we have a tool to look at least squares at a higher polynomial, all right? So for example, maybe I want to fit this data point, let's say, here's something, whatever. So let's say the original function was y equals, a1 x cubed plus b1 x squared, sorry, let's call it a2. a1, a2, a3 x plus a4, that's my function. Okay? And now, so that's what I want to fit my data to. Okay? So now, if I say ax, I want to minimize the residual, so my residual is equal to ax minus b. Okay? What goes inside the b vector for this problem? Okay, I give you a bunch of x data points, a bunch of y data points, and I'm trying to fit that polynomial. So if I was to write the residual in this form, what would it look like? B is still your y's, right? It's still your y's. The goal here is to write the residual in this form, x minus b. Okay? So in this case, we're still going y to n. We still have data points. Okay? But what's inside my x vector this time? Yeah. A1, A2, A3, A4. So what's going to be in the first row? X1 cubed times A1, and then X1 squared, X1, and 1. And then the next row is X2 cubed, x2 squared, x2, 1, dot, 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 all the way to xn cubed, xn squared, xn 1. Do you see it? So we're still minimizing, and the goal here is we're minimizing the sum of the residual squared. It just so happens that the residuals are, the variables are now 4 instead of 2. Yeah.
With least squares, do you always have to know the equation you're going to fit to?
Yes.
Okay.
Of course. Yes. Which is why when you do polyfit, you tell it what order of polynomial. You need to know it. And that the only way you need to know it so you know what your variables are.
Yeah.
You have to know that. You with me? So now if I could make up something now, a cubic, and I promise you that the polyfit would come out with the same as the P inverse A. You just have to build. The trick, again, about a lot of this class is about building, how to build A and B, and how to choose X. Okay? You're going to see it when you get in the homework, this next homework. It's going to be like, okay, what is what? Okay? I'll be seeing you guys at office hours. All right. Question. Do you see? Now, of course, there's a special condition on this to make this least squares. What's the condition? What keeps this least squares rather than something else? What's important with A and B with respect to X that makes this least squares? Yeah. It's got more equations than unknowns, so the length, it has to be a fat matrix. If it's not fat, then we're not at least squares. So meaning I have to have more data points than I do polynomial tuning knobs. Do you see that? Okay. If I only have 2 dots and I've got now 4 variables, now I'm underdetermined. If I have 4 dots and it's a 4th order or 3rd order polynomials, 4 variables, I'm now just the inverse. You see it? Okay. Okay. Questions? So now you don't need to use polyfit. All right? Now, of course, polyfit is still focused on fitting some polynomial to data points, right? Okay, we're going to try to move, now with the homework problems, we're going to move beyond fitting data points. What we're really trying to do, and this is the way I want you to look at least squares, is not fitting a polynomial with data points, but just getting a solution to M equations. Okay, we're going to solve M equations as close as possible. All right? That's really what we're talking about. So try to look beyond data points. And we'll see it in the homework. Let's see. Any other? Okay. So, if there's no more questions, let's see. All right. So now the question is, how did I build A and B? Okay. I built it by writing the residual vector, pulling out the variables, writing it as AX minus B, right? And then noticing that I'm minimizing the residual squared, okay, etc. Now, there's another way to build A. It's a slightly different view of it, all right? But I'm going to pull A and B right out of the cost function. All right, so here's another way to look at it. So let me write this. And this is an important view of it. So I'm going to write least squares again. We're going to focus on linear function. All right. Now actually, if my function is y equals mx plus b, mxi plus b, versus y equals a1x cubed plus a2x squared plus a3x plus a4. Okay. Now actually, what we've been doing is actually linear least squares. I've been writing least squares, but this is actually linear least squares. Okay? Now, this is also linear least squares. They're both linear least squares. Why? Why are they both linear least squares? Yeah?
The coefficients are all just...
Okay. They're a linear function of the variables. So just because, would you agree x cubed, well, xi cubed is a constant? That's not what our a is our variable. And a2 is our variable. So as long as you're a linear, if I can write it as ax equals b or ax minus b, if I can write ax, then I'm linear. Do you see that? So just because the polynomial is higher order, but the coefficients are linear. So this is still, both of these are linear least squares. If my coefficients become non-linear, then it becomes least squares. Okay? So these are both, even though the polynomial I'm fitting is non-linear, the variables are linear. Okay. So, all right. So let's look at the minimization. So here's how I'm going to write it. Minimize this. Let's do mx1 minus mx1 plus b minus y1 squared plus mx2 plus b minus y2 squared plus dot 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 all the way to mx n plus b minus yn. Okay. Now I'm going to take steps. I'm going to write each element as an inner product of a vector times the variable x. All right. So would you agree that this is the same as saying x1 1 times m and b minus y1. Okay? I'm changing it to inner products, plus x2, 1, m and b, minus y2 squared, plus dot, 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 all the way there. Are you okay with that? I haven't changed anything. I'm just starting to form it into vectors and then finally get it into a matrix. Okay? So now, would you agree that this is equal to, and I'm going to call this vector A1 transpose, and I'll call this x. So this becomes A1 transpose x minus y1. And now I'm just going to call y1, well, that's fine, I'll leave it y1, squared, plus A1 transpose x minus 2, minus y2, plus dot, 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 all the way to there. Are you okay with that? So now, I can easily, or actually I will, so this is now B1, and this is B2, dot, dot, dot. So if I gave you a cost function that was the sum of all these things, if you could start pulling out and put it into the inner product of some vector times the variable matrix, you can start already seeing the A and B. So now A is just built from A1 transpose, A2 transpose, dot, dot, dot. Oh, sorry, that's a 2. To AN transpose, and B is just equal to B1, dot, 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 BN. Okay, you see it? So if I give you, and you'll see this in your homework, if you've got this nasty summation, what you want to do is try to get it into this inner product form and pull out the rows of your A matrix from the cost function, and then once you have A and B, you're done, right? Because then you just do A pseudo times B. Okay, the trick is to see how do you grab A from more complicated cost functions. All right? Try to remember this technique when you look at the homework. Okay. Now, let's look at it. Let's see. Okay, we're still good. We'll have some cool. All right. Okay. Let's talk. I want to look at least squares from a whole different perspective again. All right. It's kind of an interesting perspective. All right. So I want to talk about orthogonality. Okay. So if you have, let me just draw a vector. Let's call this y. Let's call this x. And this vector here is going to be x minus y. Okay. Now again, I'm sort of drawing this because we can only see in 3D. But think of vectors. Think of the vectors as n-dimensional. All right. This is an n-dimensional space. You try to move beyond 3-dimensional or 2-dimensional. Okay. Because this is true for any. X does not have to be 2 or 3 elements. Okay. It can be much more, and this is still true and still useful. Okay. So it turns out, via Pythagorean's theorem, that x squared plus the norm of y squared equals, and when I do norm without a 2, I mean 2 norm. Okay? So the distance of the vector squared plus the distance of the vector squared equals the hypotenuse squared. Sorry, let me be clear. Those are orthogonal. Okay? Without that, then it wouldn't be true. So x is orthogonal to y. With me? Okay. Now, you believe this equation? It's just, the thing is that I'm just moving, I'm trying to write it in a form that moves past 3 or 2 dimension. But if I wrote 2D, it would just be the distance, the magnitude of that vector minus it's really magnitude of that vector, magnitude of that vector squared plus magnitude of that vector squared is equal to the magnitude of the hypotenuse squared. Okay, this is just in larger domain, larger space. Okay, well, if I write this out, it's going to be x transpose x plus, let's leave that part, actually. This one is going to be, if I write this out, it's going to be x minus y transpose x minus y, which then becomes x transpose x minus 2 x transpose y plus y transpose y. Okay. Now, of course, this is x transpose x, and this is y transpose y. Okay. Now, what does that tell you? What can you read off of this right now at this point? There's a very important piece in there. Yeah.
The 2x transpose x to y equals 0.
Right. Okay. So what does that say? It says that the inner product. So if, very important, if x is perpendicular or normal to y, then x transpose y equals 0. So the inner product, right? So we know that to be, right, if you know what the dot, this is also the dot product, right? So how do you guys remember dot product? Right? It's going to be x, y equals the magnitude of x is how they write it, magnitude of y cosine theta, right? Everybody know that equation? Dot product? Well, the dot product is the inner product. It's the same thing. So I can just write x transpose y. And if theta is 90 degrees, what do I get? 0. Okay? So they're all interrelated. Okay? But the cool thing is this is true for higher dimensional vectors. Okay? So we're going to use that. That's a very powerful little tool. Okay? All right. Now let's look at another problem. So let's look at here's my vector A. And let's just think of this as A1, A2. I want you to think about it as higher dimension. But again, I'm drawing it in 2 dimension. And this is B is equal to B1, B2, Bn. Okay? And now, I'm going to take the projection of B onto A. and I'm going to call this point P. And would you agree that P is going to be P is in the direction of A, right? But it's in the direction of A, but I need another constant. It's not all the way to point A, let's say. It's some scalar multiple times A. So x hat, and this is a scalar. It's a scalar, constant, okay? So, scalar constant. Okay. So far, so good? You buying this? All right. So now my goal is to find P. How do I find P? How do I get P? Well, what we're looking for is if I'm looking for B minus P, a vector B minus P. So if I draw, so this is going to be B minus P is right there. That vector, is everybody with me on that? That vector going from B to P, or vice, it doesn't matter, either way, is B minus P or P minus B, either way. You with me on that? Okay, and I'm looking for the point P where this is perpendicular to A. Yeah? So now I can use inner products, so that's equal to A transpose B minus x hat A. I'm looking for x, so really I'm trying to solve for x hat such that that inner product is 0. Yes? No? Stop me. I keep moving. Okay. So now let's solve for x hat. So it turns out, right? A transpose B minus A transpose, and since it's a scalar, I can look at it from different ways. So I'm going to pull x hat A transpose A equals 0. So x hat or x bar equals A transpose B over A transpose A. And therefore, P is equal to A transpose B over A transpose A times A. And it actually can be rewritten. You might see it in books as, since this is a scalar, I could move it to the other side of A, and I get A transpose over A transpose A times B, and this is known as the projection matrix. Okay? But I don't care if you know that last part. Anyways, just throw it out there. All right? So that's how we find the projection of B onto A. Questions? Good? Okay. So let's go back to least squares. All right? So least squares turns out to actually be a projection. All right, and I'm gonna prove it to you. So projection and least squares. And do you agree? I guess I should say that why is a projection useful? A projection is the point. Would you agree that the projection is the point on A that is the closest to B? Yes or no? If you move anywhere along A, you're now getting further and further away to B. So if you think about it, try to think about it, here's what least squares does. Least squares is trying to get the closest, it's trying to find an x that'll get you AX as close, whatever close means, really as close to B. All right? So what we're going to do is we're going to do a projection to find my x, which is the same as x bar. All right? So projection. So if I look at, here's what I want. I want my x1, x2, xn, 1, 1, 1, 1. And then here's my m and my b, which is my x. And then I want that to be equal to y1, y2, Okay? So here's the picture. So let's call this the column space. And when I say column space, I really just mean what is all of the linear combination of the columns. Okay? So my goal is to find some linear combination weighted by m and b. Okay? This column times m, that column times b. Can I find a combination that will give me y, the y vector? Do you agree? That's really what we're trying to do. Of course, we're never that lucky unless everything's in a straight line, right? If they follow, so some constant, if they're in a straight line, that's the only way to get there. Okay? So, here's the column space. So for example, I might write, here's my, let's say column 1. So let's call this column, this is column 1, okay, which is equal to x1, x2, xn. And here's column 2. And of course, these columns are in that plane, right? That's the column space. Column 2 is equal to 1, 1, 1, 1, ... Okay? And here's where my b is. My b is out of the plane, right? Because if it was in the plane, I have a solution, right? But in general, that's a boring problem. Least squares, there is no solution. There's no way to take a linear combination of column 1 and column 2 to get b, to get my y's, right? So the way I'm going to draw it is out of the plane. Here's my b, which is equal to y1, y2, ... yn. Okay? So what is the closest point on my column space that, or sorry, yeah, in my column space, the closest point that is to b?
So B is that entire vector. How do you pick one point on there to be the closest?
B is actually the point at the end of the vector.
Okay.
Yeah, it's the point at the end. Okay? It's just that point is defined by the vector.
Okay.
Okay? So where on the column space, where in that plane, of course this is a, is the closest point to that point B? Right. We drop down a projection. So the closest point is the projection onto the column space. Now you sound fancy. Huh? Tell your grandma to do that. All right? So let's drop this down. And here is, so, it'll be something like, we'll drop this down. Let's say that's P, which is equal to AX star, I'll say. And this is a right angle. Okay? And my column space is defined by A. So I'm looking for, so it's the same as A. I had A transpose. What did I have? Let me look at it again so we can see. I had this one. A transpose B minus X hat A. Okay? Well, I'm going to write it the same way, but I'm going to have more vectors in A rather than just one. So now I'm going to write it as A transpose B minus A X star equals 0. I want this is B minus AX star. Would you agree that I want B minus AX star inner product with A to be 0? Because that would give me my orthogonal projection. Yeah? Okay. So now I clean this up, and I'm back to A transpose B is equal to A transpose A X star, or leave the star off. Guess what we're back to? What equation is this? The normal equation. Normal meaning?
Orthogonal.
Orthogonal. Let out. Okay? And that'll give you X star equals A transpose A inverse A transpose B. The solution, the closest solution I can get is to project onto the column space. Okay. Questions? Okay. Well, let's see. I think I'm good. All right. We will. We'll start up. Well, you'll have homework on least squares. I'll hand it out Thursday. All right. We'll have homework on least squares for next week, and then I'll start least norm on Thursday. Yes.
Do you want a hard copy of our code?
No, for this homework, just Dropbox is sufficient. Okay.
What was that?
Yes. That entire plane is defined by the, and of course, this is like an n-dimensional plane or whatever, right? It's a viewing, a three-dimensional viewing of it. But yes, it is the plane that is fully defined by linear combinations of your columns.
So you're doing B minus P perpendicular to
Yep,
A.
that's right.
Homework due Thursday. Do you want us to just turn in this straight up Matlab code, or do you want us to actually show cut and paste and pictures of the various displays working as well?
No. I'll run it. So that's fine. Yep.